Good morning. Thank you. Yes. So we're going to begin with a cosmological survey. How many people in the room have actually gone and used a CCD imager at a telescope and acquired data? Show of hands. Excellent. How many people in the room have sat in the luxury of their office and reduced images that come from a CCD imaging system? How many people are completely ignorant of how CCDs work and would like to know? Well, you're in the wrong place. Okay, so my remit here is to talk a little bit about some of the idiosyncrasies of these detectors. And if you thought all that statistic stuff was bad enough, that all presupposes that we're measuring something that is an accurate reflection of physical reality. Well, this is just one completely descending bad news story from one talk to the other, because I'm here to tell you that even just making the measurements themselves is a non-trivial undertaking in the context of imperfections that afflict the sensors that we use. So let's just go through a lightning overview of how astronomical imaging systems like the LSST actually work. So the few photons that are fortunate enough to appear as information in our database rain down from the sky. Astronomy is a passive-aggressive science. You collect photons. The optical system converts the angle of arrival into a position in the focal plane and creates ideally a focused image of the portion of the sky that we are pointing the telescope at. So far, so good? Oh, yeah. Not very many. In fact, most of the galaxies that we measure are themselves fainter than the sky brightness that we are looking through. Then there's a camera system whose job is to take that distribution of photons and convert it into digital information. That happens through a chain of analog to digital converters. The LSST camera will have around 3,000 of them running at 18 bits, and this is an artist's representation of a really big data storage system. The conversion of information as photons into information as bits has an intermediate stage, which is within the silicon detector. The incident photons, some fraction of them anyway, are converted into electrons by promoting them in the semiconductor up into the conduction band. And at the wavelengths that we operate at for LSST, that conversion ratio is 1-to-1. If I were shining X-rays on this thing, I'd get more than one photoelectron per photon, but in our regime, it's 1-to-1. And the detector is itself pixelized. So there's this discrete spatial array of pixels, and what I measure is the number of collected photoelectrons per pixel as a function of time, as a function of passband, as a function of position on the sky. Good? If you take that image and make a sort of Lego plot of the cumulative, the vertical axis here is number of photoelectrons, and the x and y axes are just pixel coordinates, you get this complicated looking lunar landscape of flux distribution. And the data reduction challenge that faces LSST is to go from this two-dimensional representation of number of photoelectrons into some database entries which inform all those 2D correlation functions that we were absolutely astonished to hear about in the last two talks, right? So that data reduction problem amounts to a information representation conversion from 2D arrays of number of photoelectrons as a function of pixel integer coordinate ij into some other parametric representation of the properties of these astronomical objects. So the sort of characteristic of the optical system and the detector system that you'll hear people talk about a lot is something called the point spread function. So the point spread function is the two-dimensional manifestation of flux in the focal plane for a point source at infinity. So it's point, like it's a point, it's spread out, and it's a function. So that's the point spread function represented spatially. And one of the features that really determines how well you're going to do in any of these astronomical surveys is how broad is that in terms of angle. And basically, because the broader this thing is, the more sky photons you have to accept per point source when you're trying to measure things, and the Poisson noise in that sky background is the dominant thing that we fight. So minimizing the size of the point spread function is a real figure of merit for these systems. And you can make plots here where the vertical axis is the cumulative encircled energy as a function of radius. And these encircled energy plots, you can tell where's the 80% point that encloses 80% of the flux, and that has some diameter on the focal plane, and that's a figure of merit that engineers try to optimize. So here's a question for you. In general, for a point source on the sky, and you're going to do this with the person who's sitting next to you, this is the dynamic interactive dub applicate part of the lecture, how many parameters does it take to go from information representation as photoelectrons as a function of ij into some database representation of the salient information that characterizes an astronomical source? How many degrees of freedom do I need in order to characterize this? Ready? Go. Yes. How many degrees of freedom do I, if I'm going to make a database table, how many columns do I need in my database table per source? And oh, by the way, while you're at it, you might think about what assumptions you're making. Ideal sensors for the moment, yes.
A question about why you use encircled energy rather than encircled photons?
It's encircled number of photons. It's a misnomer. It's a historical misnomer. We don't measure energy. We count photons. We don't measure energy. We count photons. It's a historical misleading artifact. Yeah, you're right. Okay, so let's reel this in. So here's my astronomical source. Tell me the first thing you might think about measuring from this thing, and how many parameters does that take? The center. Okay, the center meaning its position, right? Yes? Which, just a sort of linguistic nuance, astronomers would call the centroid of the point spread function. Centroid. Okay? So how many degrees of freedom do I take? Uh-oh. How many degrees of freedom does it need to measure the centroid? Holy cow. How many pens does it take? There we go. Centroid. So what do I have? Oh, that's good. How many degrees of freedom here? What coordinate system do I measure it in? Oh, boy, is that a rat's nest. For now, let's just call pixel x, y in pixel coordinates. Okay? Can I measure the centroid to sub-pixel accuracy? Yes. Right? You know, they gave a Nobel Prize in biology for that simple fact. It's just amazing. So roughly speaking, the uncertainty in the centroid is the full width half max of the point spread function divided by the signal-to-noise ratio with respect to which you can measure fluxes. That's a really good seat of the pants thing. So good. So there's 2 degrees of freedom in the centroid. What's the next obvious thing that I'd like to measure? Okay, so I'm hearing a couple of things. So I've heard sort of intensity, height, flux, some representation of how bright is this thing, right? So let's call that, what the heck, we'll say peak intensity, or the integral of the number of photoelectrons, or the flux. All those are really basically saying the same thing. How many degrees of freedom is that? 1. Okay, what else? Spread, right. Okay, so tell me how many degrees of freedom I need to measure the spread of the point spread function. Oh, really? I just heard spread. If I assume it's an axisymmetric Gaussian, how many numbers does it take? Can I do weak lensing with axisymmetric Gaussians? Are we here to do weak lensing? So that can't be the right answer. So how do I reconcile this apparent discrepancy? Do I do weak lensing on point spread functions?
You said point source, right? It's a galaxy, it's not a point source.
So semi-major, semi-minor axis relative to the center. That's another 2 degrees of freedom.
Right. So basically, for whatever reason, even if the point sources are themselves not angularly resolved, it could be Chuck Claver screwed up on collimating the optics. It's astigmatic. There's charge transfer inefficiencies. Look, that's a star. Does that look axisymmetric to you? No, I don't think so, right? So let's set aside the notion of this being necessarily an axisymmetric thing, and we're going to make some model. And the typical thing that people do is to assume that it's a two-dimensional Gaussian and that it has a major and a minor axis. Okay? So if that's true, let's call that shape, right? So I need a major axis, a minor axis, and some orientation angle, right? And there are lots of different ways to cast that same kind of information, but that's a standard way to do it. Okay? So let's count. So that's 1, 2, 3, 4, 5, 6. I got 6 different degrees of freedom to characterize this thing. So does that mean I want to put all the flux in a single pixel? That would be a bad plan. Yes? Sorry? Yeah, that's right. I can take if I have an underlying model that the thing is a two-dimensional Gaussian, then I can compute that from this. But if I want to be more empirical, then I can compute intensity moments if I so choose, and I'll go you one more and say I could include flexion, because as soon as you get in the regime of doing shape measurements on objects that are angularly resolved, right, like this thing here, that's not a point source, then these are empirically meaningful. Okay? So the data reduction task then, again, just to summarize, is to go from this two-dimensional representation of information as photoelectrons in pixel space to some catalog that extracts a parametric description of each of these sources and sticks it in some database. So unfortunately, that process of information representation conversion is afflicted by the fact that detectors are not perfect. So here's a picture of the entire focal plane array for everybody loves to hate survey called PanSTARRS. And if you just look at this, does that look like, this is an image taken in monochromatic light. Does that look like a uniform, rectilinear, perfect array of pixels to you? Oh, I don't think so. So Lincoln Labs gave PanSTARRS a great gift when they made the sensors. And there are major defects from fabrication. There are entire missing elements. There's this funny swirly pattern. There are smudges and smears and crud all over the place. Okay? So what we're about here in this hour is to talk about what detector imperfections might impair that data conversion process. So a question I have for you, and you can use these whiteboards that are in front of you, are what are some of the traits of detectors which we sometimes just implicitly assume are perfect that might impact our ability to do this conversion from image space representation into catalog representation? Ready, go. You can write them down on the whiteboards. You're conferring, you're consulting, you're participating. Yeah, you, Ansari. The family, you know? Who called my name? So the question is, so let me just rephrase the question. What I want you to do is to write a laundry list of things that you assume about these detectors, which may turn out to not be perfect, right? So an example is they have no read noise. Well, guess what? They have read noise. Okay?
I don't think you have the answer. Do you know what are the main technological differences between the CMOS detectors in cameras and so on, and the CCDs they use?
Yes.
So please tell me.
CMOS detectors are not full fill factor. They're not full fill factor because the transistor occupies space, so they usually have micro lenses. They have capacitive couplings between the individual pixels that gives you spatial correlation and flux. But a lot of those properties afflict Mercatel infrared devices because they tend to use CMOS multiplexer arrays underneath them, multiplexers underneath them. So a lot of the idiosyncrasies of infrared detectors would be the things that we would see if we were to make CMOS optical sensors.
So basically, you have kind of CCD structure for potential well and so on.
You accumulate charge on one capacitor per pixel, and then you do a ripple read, and you go to those capacitors and you read out the stored charge. There's no charge transfer, but there's still a capacitor per pixel that does the charge to voltage conversion.
And the reason they call it CMOS is the electronic to
Yeah.
multiplex.
Yep. Okay. Who's got some CCD properties for me? Tell me ideal detector things. Go on, Chris. Read me your list. Linearity.
Not square.
Okay, so let's take them one at a time. So I heard linearity, right? Remember when we had that representation of the signal chain? The assumption is that that is perfect and that it is linear. Neither of those things are true, right? So the signal chain is invariably nonlinear at some level for a variety of reasons. Yes, go on.
Dead pixels, hot pixels.
Yes, the only uniform CCD is a dead CCD. Craig Mackay, late 70s. So
Blooming and saturation.
there's a certain dynamic range of charge that each pixel can store, and where do those photoelectrons go? They got to go somewhere, and they go next door. Yes?
Brighter, fatter effect, which is the change in the shape.
I like that one.
Smarter as you get fatter.
Exactly. Or
Doping variation.
it's not clear where the causal relationship is there, by the way. But yes, keep going. So we have anomalies in the point spread function where the full width half max is not independent of intensity. That's a newly discovered blank realization in the field.
Doping variations.
The silicon has impurities embedded within it that makes it depart from homogeneity.
Cosmic rays.
Cosmic rays are muons from the upper atmosphere impinging on the detector and giving you charge deposition that is not related to celestial sources on the sky. Yes?
Charge transfer inefficiencies.
When you move the charge through the array, that does not happen with 100% perfection, and you get a trail of deferred charge in trailing pixels in both the parallel and serial direction. Yes?
Readout noise and crosstalk.
Yes, so it's a little known fact. Actually, if you did well, I'll just make this assertion and then you can come and find me over lunch. CCDs actually evade the naive thermodynamic limit for how well you can measure charge per pixel using a methodology called correlated double sampling. And it is just simply magical. If you didn't do correlated double sampling, CCDs would have a read noise of about 120 electrons. And we're down at the few electrons because of the magic of the power spectrum of the read noise that we're fighting. So here's my list, which has a lot of overlap with Chris's because he must have read my overheads before he came in here. And so we assume that the pixels are square and rectilinear, but they're not. They have variable effective size. We assume it's perfectly linear. It isn't. There's this problem that the efficiency with which the detector converts light into photoelectrons is wavelength dependent. The read noise, which is how much fictitious basically, what's the variance in reading pixels if there's no light hitting them, is non-zero. We'd like to think the fill factor is 100%, but it isn't. There are gaps. We'd like to think that the optical system uniformly illuminates the entire detector, but it doesn't. There's vignetting. There's something called fringing, which comes about because light can pass through the detectors, bounce off the backside, and set up standing waves within the silicon that causes those kind of tree ring rippley patterns that are actually Newton's rings in the detector. We assume that the only source of electrons in the pixels is from light, but there can be thermal excitations called dark current that can pile up charge in pixels. We assume that the flux that we measure in adjacent pixels is uncorrelated Poisson realizations of stuff, and that is manifestly not true. We assume that in the analog signal chain, there's no analog crosstalk between adjacent amplifiers. That assumption fails. And there's all kinds of other stuff: cosmic rays, diffraction spikes, bad pixels, satellite streaks. And so the challenge in the data reduction pipeline is to somehow suppress and ameliorate these things at some level. So let's just take a look, zooming in a little bit, to a typical astronomical CCD image. And this kind of salt and peppery structured background that you see here is because of the Poisson fluctuations in the sky. So just to make that point really clearly, if I had all these pixels, each of which was receiving on average 100 photoelectrons from the sky background, that emphatically does not mean that in every single image of the sky I get 100, 100, 100, 100, 100, right? Because those are different Poisson realizations of an uncorrelated discrete process where I'm counting things. And so actually the histogram of measured sky values is a Poisson distribution. And you can see that actually just manifested here with the rattle in the sky background. So let's pull out and blow up one of these things. And here you can see some of this stuff. So what's with this little vertical streaky thing? Some people in the room surely know. Sorry? It's what astronomers call blooming, because this star is so bright that it's exceeded the charge storage capacity of the central pixel. And where does that charge go? It takes the path of least resistance, and the charge is less constrained in the column direction than it is in the row direction, and so the charge just bleeds out along the column. Okay? So look at this little tiny single high pixel here. Is that a point spread function? No, that's representative of a cosmic ray that came in and dumped all this charge into one pixel. And you can also see some things are stars and some things are galaxies. You can tell things that have resolved shape from things that don't. So the data reduction challenge then is to go through this and somehow from that crappy, so on the left-hand side is the pristine celestial sky that cosmic variance gave us. Thank you very much, right? Here it is. What we get is a fuzzy, distorted, warped, noisy, vignetted image with cosmic rays, diffraction spikes, and crosstalk. But luckily, who do we have? Jim Bosch and his colleagues. There he is, right there. Jim, this is your problem. So the data reduction challenge is to take this crappy version of reality and suppress the sensor artifacts and somehow produce some representation that is closer to this than it is to that. That's one phase of the image processing. And the next stage then is, after you take this artifact suppressed image, to turn some crank that goes from this pixel space representation to a catalog representation of the properties of sources, where we now have put the centroids in actual celestial coordinates. We've given a time tag, we've measured a flux, we've measured uncertainties, measured the sky background, we've measured ellipticities with amount of ellipticity and some orientation. And I would like to ask someone in the room to just very briefly, in 3 sentences, tell me what measurement constitutes doing weak lensing science. How do I actually do weak lensing from this catalog? I don't do it from the image space representation. How do I take cataloged information and write a weak lensing paper? Yes? 3 sentences.
Measure ellipticity of galaxies in the image behind your cluster.
Okay, so I have to repeat this because there are some people listening online. So the first sentence was, measure ellipticities of galaxies, and then you said behind your cluster, which presupposed that we were doing cluster weak gravitational lensing. So we're going to push that aside for a second because that's narrowing our scope. So determine an estimator of the ellipticities of galaxies.
Average over all galaxies for which you've measured an ellipticity. Any residual tangential ellipticity can only be caused by some non-zero gravitational potential.
Right, so that Sure, I'll take that. So basically, take those measurements of ellipticities of objects, do some kind of redshift and spatial processing and filtering, and then from that deduce what the line of sight mass distribution is, which introduces distortions of shapes of objects, right? I'm assuming everybody here has seen Tony Tyson or other people's weak lensing qualitative picture of the distortion of shapes of galaxies, yes? But is weak lensing the only thing that distorts shapes of things in astronomical images? What if the bore side of the telescope, not that this has ever happened in the course of human history, but imagine there's an oscillation in the pointing of the telescope, so it's going dig, 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 dig. Does that introduce ellipticity in objects? Yeah, baby. And is that typically bigger than the ellipticities that we're trying to measure in weak lensing? Yeah, baby. So how am I going to deal with that? Please.
Identify stars in your field which should have zero ellipticity and use those to characterize very precisely spatial dependence of your portrait function.
So that is the legally appropriate authorized party line, which is use the stars to correct for the ellipticities that don't come about from weak lensing signals, and that's great, except for, number one, you just assumed you could do perfect star-galaxy discrimination. Bam. Number two, you assume that the point spread function that you extract from stars is directly applicable to galaxies. Bam. Because we just told you that the full width half max depends on intensity, and what is the first thing these weak lensing scoundrels do? Where's Doug Applegate? There he is. What is the first thing he does? He says, let me find the really bright high signal noise stars and use those to really get the ellipticity to a gnat's eyebrow. Well, guess what? They don't have the same shape as the faint sources do. Bam. Okay? So this is not a trivial undertaking. Okay? That's the message. And thank you very much for your complete and comprehensive cluster weak lensing answer. So, right, so the question is, okay, so lest we leave the room terrified and horrified and quit the project, is there a way to compensate for this intensity dependence of the full width half max? And the answer is sure, measure it, right? If we can characterize it, we can correct for it. And part of the challenge in the dark energy science collaboration meeting that's happening for the rest of the week is to create a path to actually understand, quantify, and suppress those artifacts. We suppress all kinds of other image processing artifacts. We can suppress this one too. Ain't that right, Jim? Yeah, baby, says Jim. Boov.
Chris, what is your 3-sentence description of measuring the lensing from this catalog data?
Call Boov on the phone. Do what he says and beg to be a co-author. So, but that, look, that's the challenge, right? The challenge is how do we go from these parametric descriptors of properties of objects to a three-dimensional mass map, because that, as you learned from the previous talks, is the goal of doing cosmology with these imaging data sets. So it's an interesting question as to, let me try, where's Michael? Michael's here, so I'm going to try and do this, okay? So the question is, what is the most reliable, unbiased estimator of the lensing perturbations to the shapes of objects, given that you have multi-epoch and multi-band image of the sky taken under different conditions and air masses, right? How do you take that stack of images and construct an estimator? And the historical weak lensing analysis has kind of gone, la, 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 I'm only going to take one image at a time. I've never looked at the sky before. I only have this one passband, and let me go and measure a shape. Okay? Sorry for all you weak lensers in the room, but that's essentially what they've done. That sounds to me suboptimal. So that's a question for another day. So my question is, the weak lensing signature is the artifact-corrected shear map as a function of position in 3 dimensions. The supernova dark energy signal is really this peak flux as a function of redshift across different passbands. So for those 2 dark energy probes, you're asking all the right questions. How do we go from the aggregate data that we have in image and catalog space and arrive at cosmological contours that we believe? Sir?
Can I throw, so if you want to get rid of biases, you can't do better than marginalizing over all the inputs to your signal when you will care about it. And that means, is there any hope of modeling or predicting this to such a degree? Not just the signal, but the distributions of the signal, so the correlated distributions in a way that you could ever think about that.
Yeah, great question. That's how we should all be thinking. Reza's going to say yes.
No, I was going to say that we should be careful about not putting everything in statistical distributions because that will prevent us of understanding a number of effects. If you say, okay, I have characterized my distribution, and you know better than me, but just by its sigma squared. And if you don't look to the tails, then yes, you compute the sigma squared and you don't see that.
So for people listening online, I would say we have devolved into a philosophical meta-conversation about methodologies for optimal weak lensing analysis, which is outside the scope of this hour. So this we said already, you know, basically we do end up using the PSF from stars to make some correction to galaxy shapes, and we need to be careful to do that properly. And we're going to spend the rest of the time that we have together thinking about one particular source of systematic error that might afflict that process and how we might go through the process of coming up with a quantitative entry in a systematic error budget for the weak lensing signal. Okay? So we're going to go through that as a toy exercise. Sound good?
Yeah, baby.
Okay, so let's talk about charge transport anomalies. So here's the ideal CCD, which has a completely rectilinear array of pixels of uniform sensitivity, equal area, and a perfect grid. For reasons that Andrei Nomorotsky and other people in the room can tell you about, that isn't how it really works. There are charge impurities, and as the photoelectrons make their way from where they are created down into the pixels, they don't always go in a straight line. And they get bent because of lateral electric fields that are within the silicon. And so there's a two-space to two-space mapping function that essentially means that you get a distorted image of the sky with rubber sheet distortions on different spatial scales. Are you with me? So I could make a two-dimensional plot. If this is just, if I'm only going to introduce perturbations in the x direction, and the y direction is completely rectilinear, I could make a map of the amplitude of this distortion as a function of position in the focal plane. And that's what that is, right? It's a map of the perturbation field. Yeah. It depends on the origin of these perturbations. The impurity-driven perturbations, which are called tree rings that are quite apparent in the dark energy survey, are greatly suppressed in the LSST sensors. Okay? It's below the part per thousand level. But let's go through the exercise. So this is this pictorial representation that is, as these photoelectrons come down, you have to realize that the LSST pixels are themselves skyscrapers. They're 10 microns on a side and 100 microns high. So the aspect ratio of an LSST pixel is 10 to 1 in the vertical direction relative to horizontal. So there's ample opportunity for these puppies to get moved laterally. And believe me, they exercise that opportunity. Yes? Why are the pixels so thick is a great question. And there is a physical scale in the problem, which is the absorption length of light in silicon. And silicon is essentially transparent to photons that have wavelengths beyond about 1.1 microns because each individual photon just does not have enough energy to do the quantum mechanics of moving the electron up into the conduction band. Okay? So as you get closer and closer and closer to that inability to generate photoelectrons, the silicon becomes more and more and more transparent. So if you want to build an astronomical imager that's sensitive to near-infrared light, you want to make a thick one. And it's a trade-off between augmentation of sensitivity and image degradation because of a variety of effects that scale with the thickness of the sensor. And the optimization choice that was made for LSST is 100 microns thick. And the size in the other direction is to give appropriately sampled point spread functions under the best possible seeing conditions given the focal length of the telescope. So that's what sets the two scales. Great question. How would you improve which limit? Well, the sensors that are used for the dark energy survey are twice as thick. They're in a telescope beam that's not as fast as the LSST beam, and the plate scale is a little different. So this sort of trade-off in sensor thickness is a system-level optimization problem. I'm not sure I answered your question. Off topic, moving right along. Well, the answer is yes, people made germanium detectors, but they don't like to make germanium as silicon fab lines, and it's prohibitively expensive to do at this scale. Sir?
Would it be crazy just to stack two 50-micron sensors?
Yes, because the second one's not in focus. Okay, moving right along.
Potentials at the space between the two pixels, right? So here it's long, you've got plenty of space for potentials to develop at the interfaces. Now you've got double the number of interfaces if you stack two pixels, right?
So a more interesting question, David, is people have made layered detectors where they tune the quantum efficiency to get some kind of chromatic information. A company called Phoveon has made CCDs that do that. One thing that I will take this opportunity to correct is that we often convey the impression that the red photons are converting preferentially down here, low down in the detector. In this picture, the light is coming down from above. But what's really happening is that the residual intensity of photons looks like I times e to the minus z over z naught, right? It's exponentially decaying into the volume. So for all wavelengths of light, the majority of the photons convert up here at the top surface. It's just that more and more of them survive into the bulk for redder wavelengths. Okay? But this is not an engineering CCD thing. So here's my question. If we do imagine that one source of systematic error that afflicts these measurements is this two-space to two-space mapping function from coordinates of the sky manifesting in pixels in a distorted way at different spatial scales in both the x and the y direction, what the heck are we going to do? What combination of laboratory and on-sky measurements, oh, right, and in case I didn't say it, right, just to be clear, what happens if I put circular point spread functions down in this warped space? Do they remain circular? So does this warping induce shape perturbations to what I'm measuring? Yes. Are they spatially coherent? Does that sound like a problem? Do I have your attention? Okay, so what in the heck are we going to do about it? So this is another question for people to work and talk through together, which is what combination of laboratory and or on-sky measurements are we going to hand to our colleagues in data management to allow them to produce pristine catalogs that are uncontaminated by this non-ideality? Michael.
Can you tell me what to assume about time dependence?
Assume it's time independent. Assume it's time independent. So if there's a time independent two-dimensional mapping function, you know, we've dealt with this before, right? The optics induce distortions in that mapping function, but they tend to be very low-order polynomials that are axisymmetric around the center of the optical system. That is manifestly not true here, okay? And in fact, I'll tell you that some of these spatial scales are on the scale of the point spread function, which is maximally bad, okay? So the question is, what are you going to do about it? You're in charge of LSST data management. Tell me your plan. Ready, go. The answer is use the DES pipeline. You should talk to him. He has to do it. You should talk to Jim. He's the guy who has to actually do it.
I think, if you could do it on the CCD in the lab before you put it
Sorry?
different answer depending on the spatial scale? I guess we'll find out shortly.
Bigger effects are different, effects per pixel are different to effects.
What is the most insidious spatial scale? Almost. The spatial scale of the resolved objects on which you're doing with lensing. Right, because they're the ones that are going to get perturbed.
You don't just care about the VAO, you care about VAO as well, and that spatial scale is more or less the focus, right?
I don't disagree with you. In fact, we care about all spatial scales because this actually perturbs our flux calibration, and we want cross-focal plane flux uniformity at the sub% level. So it goes from focal plane spatial scale to pixel spatial scale and everything in between. Makes you want to go do collider physics or something. It's amazing the damn thing's ever worked at all.
Collider. It might make you want to go to a lepton collider. I don't think it'll make you want to go to a hadron collider. Linear cycle is not really a big deal. It's whether you're colliding electrons.
Yes, ma'am.
You had a table on a slide, like some slides back, that said all these different things that are problems with the image, listed under, CCD effects. But
Yep.
some of those included vignetting, which is not the camera, that's the...
It's the system. It's the system.
So when we're talking about distortion, we're talking about the system.
Sure. Yes. Sure. The optics induce distortions. Yep. Okay, you have a management plan, you have a cost schedule, budget, and work breakdown structure, and you're ready to go, right? So, to my mind, there's a big fork in the road here, where if I only ever had one image of the sky, I'd have to confront this, right? If I only had one realization and only ever took one picture, I'd better be able to undo that two-space mapping function. Otherwise, I'm just dead in the water. I mean, I just don't see a way around that, right? Yes? You with me? But does LSST only take one picture? Why, no. We have an ergodic sample of hundreds of images with dithers and rotations. And, oh, by the way, are galaxies round in the first place? No, right? So galaxies have already intrinsic shape noise. So this is just adding on top of that something that's locked into the focal plane, right? So one approach would be just hold your nose, dither like heck, and hope it averages away. Okay? Yes? What's wrong with that? Why is it sensible to me? Right? How much residual print through? It's an eminently rational approach. Way down, way galaxies. What the heck? So that's the fork to the left approach, right? Would be to say, well, it may be that I'm looking at lots of different, but if all this is frozen, I'm trying to just build a data analysis, unknown perturbation that's locked, superimposed on stuff, and find my friends who know about Fisher matrix, likelihood fit, that allocate focal plane, and I don't care what they came from, to fit them out. Right. I think in principle there's actually nothing wrong. It's a pragmatic question of is the residual print through Phil? Yep. Oh, well, yeah, rhythmic perturbations to shape of ellipticities of galaxy blending. Oh, there's a whole. So two. So one was just the second is be a little fit. The more let's actually tail somehow forcing Tony Tyson of 189 of 16 million pixels into a point source back and forth across spatial resolution and then invert it. I'll go call him. I'll tell him he has to. Or we could say, well, there's this pretty well these days, and they've got this, give me an astrometric catalog of pico arc second. Why don't I just take that and determine this mapping function, looking at the vector field of astrometric, the aggregate of all images, and then sky. What's wrong with that? and actually dynamic range of, right, because we saturate as good as you might want. So maybe images of brighter sources, but that's, so all those are in, right, and anything else that you may. Let's talk about how you might programmatically make an assessable, I mean, computational simulations, how these perturbations impact, okay? So I'm going to give, look, I went to this talk by this dad, he had these rainbow plots, can't measure the shape of anything. It's you quantify that this introduces the shape or the ellipticity. I'm asking you to just sketch out a little block diagram of computation undertake in order to arrive at a systematic error budget. How be hard-nosed about it? How would you quantify parameters you think are important that are introduced by these two dimensions? Okay, so just sketch.
Think about
5. I'm on track. Sorry? Well, let me read here. So, given two function, which pretend like, okay, the question is how that contaminates physical sources.
I want to congratulate you as the pitch for running LSST time while lecturing. Beautiful.
Never miss an opportunity. Your attention to the pun of the day. Can I have 5 more? Because this is. So before we sort of pause for a second, to sort of, I mean, you know, seat of the pants guy. I like to get some kind of physical, I'm just at a loss. And so from the perspectives, as a spatial scale here, okay? So if I were to draw two-dimensional space, distorted circles in this it's really the spatial grid of what's happening to me, right? 0, the perturbation is minimized. Locally, the mapping is flat. Perspective in mind, if I had select much larger length of these perturbations, a large distortion of my, it would produce high frequency of the object. Approximation, I'm basically imposing all wash out, right? On really fast scales, this is not, right? What if the spatial scale is long and my produce a big perturbation? No, because I'm in the omega comes out if you want to think. So if I were to just from the seat of the pants plot as a function of wavelength for very short wavelengths, S problem, for really long big problem, but there's this, what sets this spatial? Yeah, this is the only sound is the angular size of the thing. So I went and basically in MATLAB, so that's the equation for a circle. Stay totally seat of the pants, kind of distort the coordinate system, and of different definitions. Definitions of ellipticity, that I used. Physicists don't even agree among sub. I could imagine measuring a function of the ellipticity per function of the spatial, right? And I could literally engineer measure transformations and document spec on the ellipticity residuals for LSS. This quantity being to give you a sense of scale. Interested in part per thousand, that should give you, okay? So I just went through the images on the right in black and the three in blue. Scales. So here's where this is short. Here it's equal, and here the perturbation length scale is more. The right-hand side are as a function, right? So Haitians in the is actually a fit to which is my seat of the pants way to S. You can just go through and base delta R perturbations, residual Fourier component ellipticity, and make it function of spatial period, city perturbation. And what you get on the board over there, which is spatial period. So this is short period. So at high frequency, low pass filter it. So here's this, just like we thought would happen. And when the suppressed, because the wavelength is in this regime, and then aliasing, where they be at quadrupole terms that have non. And I did a spatial out, but this is how you doing something in FOSIM, in LSST. You'd basically image of the sky, introduce lensing analysis, turns, and call that the systematic. Jim over there and say, boy, you'd better 4 parts per thousand. And that kind of enterprise collaboration is organized to arrive at a quantity for a multiplicity that perturb not only shape measurements. Okay? I don't have time to do this, but I would base assumptions underpin the conventional ellipticity corrections, local PSF that's intensity long. Are they valves of sensitivity, and how do you know? Our collective challenge is systematic error budget, and we can for sensor effects. Michael? I didn't even bother. I mean, that should come out, right? So, these slides are from Andre. Gradients in the dark energy. And if you make a radius, the surface brightness in a flat, you make a similar plot, perturbations of the positions correlate with one another. So, right? You can go in and dimensions, which people have observed, map out that vet within FOSIM, and say, well, what we care about is the function and actually assessments of how that impacts time.